In section 6.2, I'm going to discuss static friction. Static friction is the form of friction that keeps surfaces from sliding past each other. And anybody that's ever tried to push a heavy dresser across their bedroom floor knows that it's harder to get the dresser moving than it is to keep it moving. The thing that you have to do to get it moving is overcome static friction. It's the stronger form of friction. But it's also the complicated form of friction. Kinetic friction just has one equation for it. Static friction doesn't really have an equation. So, to build a little bit of intuition and experience with it, let's consider a box that's at rest on a floor. And a student comes across and starts pushing on it with an increasing horizontal applied force. So, when we consider the forces acting on the box, we've of course got the weight acting down and the normal force exerted by the floor on the box acting up. The student is going to have an applied force that pushes to the right. And as a result, if the box does not start moving, there's going to be a frictional force, and it's going to be static friction to start with, preventing the box moving to the right. So that friction force has to act to the left. So let's say that the student pushes with 10 newtons and observes that the box remains at rest. Well, what's the value of the static friction force? Well, if the box is remaining at rest, that means that the box is going to have forces on it that are acting in balance. So the static friction force is going to have to equal the value of the applied force. It's going to equal 10 newtons. Well, let's say if the student pushes with double the force and she observes that the box stays at rest. Well, same thing. The friction acting on the box is going to have to be 20 newtons. How about the applied force of 30 newtons? Well, if the box remains at rest, the friction will adjust itself to be 30 newtons. How about 40 newtons? If the box remains at rest, it'll be 40 newtons of friction holding it at rest. If the student pushes with 50 newtons and notices that the box begins to slide, well, what's the friction then? Well, then the form of friction is kinetic. All right, it's going to be sliding, so we now have kinetic friction. And what's the value of it? Well, we need to know the acceleration to determine the value of the force of kinetic friction. And we learned how to do that in section 6.1. Determining the direction of static friction can be very tricky, but here's a few rules to make it a little bit clearer. Static friction always acts parallel to the surface of contact, the same as kinetic friction does. Here's the tough one. Static friction is always opposite the direction that the object would move relative to the surface if there was no friction. So there's two basic situations where you might have to decide which way it is. The first is if you have a surface that's at rest, like an object on a floor. And this is a little bit easier because it's opposite the direction that it would slide if the surface was frictionless. The difficult one comes when we have a moving surface, like the floor of a moving car. Here, the force of static friction acts in the direction of the surface's motion. So if you think about your car, when you accelerate forward, the objects in your car have to accelerate with your car. Something has to move them forward. It's the friction with the floor of your car that moves them forward. So the second situation with the moving surface in bullet point B, that can be a little confusing because friction acting in the direction of motion, that sounds a little bizarre, but that's how it works. This slide's going to go over how to calculate the magnitude of static friction. And with static friction, there's several important properties that you have to keep in mind. The first is that static friction is stronger than kinetic friction. It's harder to get something moving than to keep it moving. The second is that static friction is a variable force. It's going to adjust itself automatically to provide just the right amount of force so that surfaces don't slip past each other. There's no equation that I can give you for static friction. You're going to have to set up a net force equals ma equation based on all the other forces that are acting parallel to the surface. It's very common to see an acceleration of 0 parallel to the surface when static friction is involved, but not always. And the third property is that static friction has some maximum value. And we have an inequality that we can use to calculate that maximum value. Here it is. That maximum value is a quantity called mu s. Mu s is the coefficient of static friction times normal force. And so we have a value for the maximum value that static friction can take, but static friction itself does not have to equal mu s times n. It's just the maximum value that it can take. Really, static friction is defined by an inequality. If this inequality is violated, if static friction becomes greater than this maximum possible amount, then the object will begin to slide along the surface. Time for some examples. In this first one, we have a student that pushes a stationary 30-kilogram box. We should recognize that 30 kilograms is the mass of the box. The coefficient of static friction between the box and the floor is 0.75. We should recognize this as mu s, the coefficient of static friction. We're then given the coefficient of kinetic friction as 0.50. We should recognize that as mu k. We are to calculate the magnitudes of all the forces if the applied force is 200 newtons. Okay, we'll handle part A first, and then we'll look at part B when the applied force is 250 newtons. So all the forces acting on the box. Let's draw a free body diagram. Acting down will be the force of gravity, called weight, and we can calculate that force. Weight is mass times g. We know the value of the mass is 30 kilograms. We know the value of g is 10, and so the magnitude of the weight force is going to be 300 newtons. The floor is going to exert an upward normal force, normal because it is perpendicular to the surface of contact, and there is no motion vertically. Therefore, the forces vertically have to be balanced. They have to equal each other. And so the normal force is going to equal the weight and is also going to be 300 newtons. Now there's going to be an applied force pushing forward, and in part A, that applied force is going to have a value of 200 newtons. And if the box is going to remain stationary, if the maximum value of static friction is not exceeded, then there's going to be a backward static friction force. So the first step is we want to figure out what that static friction force would be if it were static friction. If it were static friction, the acceleration would be 0. It wouldn't be moving, and therefore the static friction force would have to equal the applied force and would be 200 newtons. But we have to check, does this value exceed the maximum possible value? Is the magnitude of static friction less than or equal to mu s times normal force? Okay, so let's check that this inequality is still is not violated. So the magnitude of static friction is 200 newtons. The value of mu s is given as 0.75, and the normal force we calculated to be 300 newtons. Evaluating the expression on the right-hand side of this inequality, we get 225 newtons. So the inequality is not violated. This is true, and so the static friction force will adjust itself to be just enough to keep the surfaces from slipping. And so the static friction force is going to equal the applied force and is going to be 200 newtons. On the next slide, I'm going to do part B to consider, well, what happens if the applied force is now 250? Well, if the applied force is 250 newtons, that exceeds this maximum possible value. This inequality will be violated if we consider the applied force to be 250. And so the box is going to begin to slide. Okay, so in part B, we're considering the applied force to now be 250 newtons. So in this case, the static friction force will not equal the applied force because now we're not going to have static friction. Now we're going to have kinetic friction. Why is this? Well, now if it were to stay in place, the static friction force would have to be 250 newtons, and that violates this inequality. And so it's going to begin to slide, and now we have to use the equation for kinetic friction. The friction is going to be the kinetic form that only takes one value. And the force of kinetic friction can be found by multiplying mu k, which is 0.5, times the normal force, which is 300 newtons. And so the kinetic friction force is going to be 150 newtons. And notice that the force of kinetic friction ends up being less than the maximum static friction. That's a demonstration how static friction is stronger than kinetic friction. Okay, here we have a 2 kilogram box that's held against the wall, and we need to determine the direction and magnitude of the force of friction acting on the box. So here's a free body diagram for the box. We'll have the applied force pushing into the wall. We'll have the weight force acting down, and we can calculate the weight force by multiplying the mass times g. We're given the mass as 2 kilograms. G has a value of 10, and so the weight is going to be 20 newtons. Now, this one's a little bit different because here we have a vertical surface of contact. The normal force is always normal to the surface of contact. So here, normal or perpendicular to a vertical wall would be a horizontal force. The friction is going to have to act up. Remember that static friction always acts parallel to the surface of contact. So parallel to a vertical wall would either be up or down, but static friction is going to have to act upwards to prevent the box from slipping down the wall. And if it is to stay stationary and not slip down the wall, all the forces have to be balanced. The forces in the horizontal direction will have to be balanced, and the forces in the vertical direction must be balanced. And so the force of static friction is going to have to equal the weight of the box, which is 20 newtons. Now for part C, we want to know the least force that's going to prevent the box from slipping down the wall. We're given the value of mu s, the coefficient of static friction. And so we're going to have to make sure that our inequality, that static friction can't be greater than mu s times n, is not violated. So we know that the static friction has to be 20 newtons. It has to equal the weight of the box. We know that mu s is 0.4. And we know that the normal force has to equal the applied force. So this inequality cannot be violated. It has to be true. And when the right-hand side is as small as it can be, when the applied force is a minimum value, that's when this inequality becomes an equal sign. It becomes an equality, an equation. So 20 is going to equal 0.4 times the minimum value that the applied force is going to be able to take. And so the minimum value for the applied force is 20 divided by 0.4, or 5 newtons. And for our last example, we're going to do something a little bit different here, where we have a box of mass M that sits in the bed of a truck. Most problems, the mass is going to be given to you. If If you ever see a problem where the mass is not given, that's probably because the mass is going to end up canceling out within the problem. So don't get intimidated when the problem does not give you the value of the mass. It's because it's probably going to cancel out somewhere in the problem. We're given the coefficient of static friction as 0.5, and we're given the coefficient of kinetic friction as 0.3. And we wanted to determine the maximum acceleration of the truck such that the box does not slip on the truck bed. What we're trying to find here, we're trying to find the maximum acceleration where this inequality is not violated. If this inequality is violated, that means that the box is going to begin to slip, and the truck is going to accelerate forward faster than the box accelerates forward. And so the surfaces are going to slip past each other. So we're going to start the problem off just like we do every force problem. We're going to draw a free body diagram. Here's the box. It's going to have a frictional force pushing forward. It's either going to be a static friction force if we have not exceeded the max acceleration, or in part B, when the truck accelerates at a rate of 8 meters per second squared, that, spoiler alert, is going to be greater than the maximum acceleration for the box to not slip. And then that would be kinetic friction because the box would be slipping. There's going to be a weight force acting down, and I will remind you that that weight force is going to equal the mass times g. And then upwards, we'll have a normal force, and the normal force is going to have to equal the weight because the box will definitely not move at all vertically. So vertical forces have to be balanced, and so the normal force will also equal mg. So we'll start off with the net force equation. The net force is going to equal ma. And here we're going to be focusing on x direction forces. There's only one x direction force. It's the force of static friction. And this will have to equal ma. So in order for the box to not slip, the inequality for static friction cannot be violated. Static friction has to equal m times a. So I'm going to substitute m times a for static friction force. And that value cannot be greater than mu s times normal force. Well, I have an expression for normal force. Normal force is m times g. So I'm going to make another substitution. I'm going to substitute m times g for normal force. And here's the point of me not giving you the value for the mass, because the value of the mass does not matter. A heavy box or a light box would start to slip at the same acceleration. So we're asked to find a maximum acceleration. A maximum acceleration would mean this left-hand side is the biggest value that it can be, such that this inequality is not violated. And so the maximum acceleration is going to happen when it equals mu s times g. And we have both of those values. Mu s is 0.5. G has a value of 10 meters per second squared. And so the maximum value of the acceleration such that the box does not slip is 5 meters per second squared, which is why in part B, when the truck accelerates at 8 meters per second squared, the form of friction that we're going to have is going to be kinetic. I'm going to need a little bit more room, so I'm going to go to a new slide to do part B. Okay, so if the truck is accelerating at 8 meters per second squared, the form of friction is going to be kinetic friction. That's still going to be pushing the box forward. The weight is still equal to mg. The normal force is still going to equal the weight, and it's still going to equal m times g. So again, for the box, we'll have F net in the x direction equaling m times a. The net force in the x direction is going to be kinetic friction. That's the only x direction force that is acting, and that's going to equal ma. A little bit of side work to do. The force of kinetic friction is equal to mu k times normal force. And I can make a substitution for the normal force. The normal force is equal to the weight, which is equal to m times g. So I can substitute in m times g for the normal force. Now I can bring this expression over and substitute it in for the force of kinetic friction. Kinetic friction is mu k times m times g, and that's equal to m times a. Notice there's an m on both sides of the equation. I can cancel out my m's. And when you cancel, keep in mind what you're doing is you're really dividing both sides by the same thing so that m cancels. And we're left with acceleration is equal to mu k times g. Mu k is given as 0.3. G is 10 meters per second squared. And so the acceleration of the box is going to be 3 meters per second squared. Notice that this is less than the acceleration of the truck. The truck is going to accelerate much faster than the box, and so you're going to see the box seem to slip towards the back of the truck and then eventually fall off the back of the truck. Okay, to wrap up the lecture, I want to show you a demonstration that everybody's seen. It's the classic tablecloth trick. You've got some things on top of a tablecloth, on top of a table, and if you pull the tablecloth hard enough, it accelerates fast enough so that the things on the table, which have inertia and don't want to move, just simply fall straight down and aren't sent flying everywhere. So the idea is she needs to pull it fast enough so that it accelerates. Well, here's the things on top of the tablecloth, and here's the tablecloth. How fast does she need to accelerate it? Break it down, let's look at the forces acting on the items on top of the tablecloth. They all have weight that acts down. There's a normal force exerted by the tablecloth up that should be equal to the weight, that should be equal to mg. And if the trick is going to fail, there's going to be a sideways frictional force that pulls the items along with the tablecloth. That would not be a good thing. So the net force is always going to equal ma, and if this trick fails, the net force is going to be a static friction force, and this inequality will not be violated. So in order to perform the trick, she wants to violate this inequality. She wants the acceleration to be so fast that this is the inequality is violated. So if we insert m times g in for normal force, notice that we have an m on both sides of the equation. Just like we saw in the last example, we can cancel the m's. And if she is to violate this inequality, we need the left-hand side of this inequality to be bigger than the right-hand side. And so as long as she accelerates faster than mu s times g, then the inequality will be violated and we'll have kinetic friction, which is much weaker than the static friction. So how quickly she needs to accelerate it really depends only on one thing. It depends on mu s between the objects and the tablecloth. And this is a function of the types of materials that she has. If we have materials with a very high mu s, so if they were lined with sandpaper, this trick would be unlikely to be successful. If you had surfaces with a very low value for mu s, so if she coated instead of a tablecloth, she was using something like a sheet of plastic coated in oil, then she'd be very likely to be successful in this